Hey everyone. So I apologize. This is the first time through this talk, so the voice track might be a little rough, but bear with me and we'll get through it together. So first I want to say, yes, I'm Dom Rizzo. I want to say thank you for having me. I really appreciate the invitation. As was mentioned, I do wear a few hats. One is the CEO of this new startup, focused on trustworthy security, zeroRISC. The other is the reason I'm here today. I serve as the project director of OpenTitan. So just getting right into it, what is OpenTitan? It is the world's first open source silicon root of trust. We also think it's the most active open silicon project that's out there today. I'll get into the numbers behind that in a little bit. So I'm going to talk about some kind of major milestones we've recently hit. One is the RTL freeze, which is going to result in engineering sample chips this year, which is the precursor to actual commercial silicon next year. The other is our integrated root of trust design, which has actually been under development for quite some time, and it's coming shortly. And extensively a bit, I'm going to discuss how our Silicon Commons approach has really led to it's basically allowed us to create a very robust collaborative framework and gotten us to where we are today. So RTL freeze, shuttle tape out this year with chips back, really based around these three principles of transparency, flexibility, and quality that has been kind of a through line from the start. And I'm going to weave that into kind of discussing, where we came from, where we got to, and where we're headed. So, what have we been doing for the last 5 years? This has been around for a while. In the public for about 4 years. It's actually been going quite a bit longer than that. And how do you go about building a commercial chip in the open source? So even a small commercial chip probably requires 50 people over multiple years. When you do it in the open source, when that hasn't really been done before, that really only magnifies the effort. And so you need to really put in place an organizational structure, a strong framework from the very beginning to succeed at the scale of coordination that is required. So kind of walking through our scalability journey a little bit, this actually started, we'll say 2018 with the formation of the Silicon Transparency Working Group, lowRISC, Google, ETH Zurich. Really, I pitched what became OpenTitan probably starting in 2016, so it takes a while to land these things. But 2018 is really when we had those first set of formal partnerships. So Silicon Transparency Working Group is a bit of a mouthful, so we quickly pivoted and called that OpenTitan. But you can see from the very beginning, if you look at these kind of blue highlighted milestones, those are sort of coordinating items. Those are the things that are required to really be able to work successfully across this diverse set of organizations, this diverse set of people towards a common goal, a large-scale engineering effort. And if you notice that first year, really focused on putting in place that framework, this notion of comportable IP, which is just to say structured interfaces, structured documentation, things that reduce the long-term maintenance burden that allow for the individual IP blocks to really play nicely together. So, this eventually turned into what became what we call the Silicon Commons, which I'll talk about a bit later. But that's what really allows us to work together in this large distributed fashion. So what are we actually building? Well, the first chip is codenamed Earl Grey. That has a lot to do with the fact that it's sort of overseen by this low-RISC organization in the UK, so we went with T themes. So what this is an OpenTitan discrete piece of silicon. So, we often call it a root of trust. Even people on the team will often call it a root of trust. But the root of trust is really just an application that is running on one configuration of OpenTitan ecosystem IP. Right? Rapidly reconfigurable. There's lots of other applications. We just kind of use shorthand as the root of trust because that's really the driving application that motivates this need for extreme transparency. So this design, this discrete chip, this first top level is hardened against physical attacks, and it has been designed from the beginning to meet these commercially relevant certification guidelines, the FIPS 140-3, the Common Criteria PP84, secure element protection profile. So a lot of thought has gone into kind of designing this chip to meet end use cases that do require these formal certifications, that do require sort of a lab-based analysis. So it's not just that, oh, well, we've got a KMAC. It's that, well, we've got hardened IP in there. We've got a hardened big num engine. We do all of those kind of necessary design features to meet the advanced vulnerability analysis requirements. So I was going to do a click-through demo here. I'm not, but I'm still going to call ahead to Greg Chadwick's talk tomorrow on IBEX, which is another key OpenTitan block. Strongly recommend people go and see that. I happen to know that that core has been taped out many, many times, and it's actually derived from the zeroRISC core, which is part of Pulp. So this is all built from the contributions of many, many, many engineers. So this is a demonstrably active project. There's not a lot of bit rot here. On a monthly basis, it's tens of organizations, about 10 organizations, tens of contributors, hundreds of commits, issues, and PRs, building up to thousands of file changes, 10,000 individual edits. And this is not an abnormal month, even though it is a kind of a milestone month for us. So, and this also excludes all of that kind of people management, program management, coordination, business side, downstream integration. So the number of people who are interacting with this project on a month-by-month basis is probably 2 to 3 times what's actually shown in the upstream commits. And this is typical. This is not an abnormal month, right? And so you can see in aggregate, this leads up to just literally 1 million+ lines of source code. And it covers everything from the continuous integration infrastructure all the way down to the actual RTL, the HDL design itself, and the design verification. It's not just people contributors. All of those engineers that are working on this, they all need to be paid. So what we've done is we've really brought together a set of companies, a set of organizations with very diverse business goals. Very few of these companies are actually attempting to get the same exact thing out of this project. They're each taking bits and pieces to meet their individual goals. There's this misperception that open source is free. That's just not the case. Our view is more that open source is about creating a commons and then actively maintaining it to keep it from becoming a tragedy. So it's about shared cost for commodities, not no cost, even if it might seem that way just from the surface. So in our case, we have worked with the lowRISC organization, this UK-based nonprofit, to help orchestrate and oversee all of these activities, all of this individual OpenTitan project. Now, they have their own independent engineering team. They're responsible for maintaining this common development space and sort of bringing together all of these partners in a copacetic way so that we're all moving forward together towards a single large engineering goal. So they oversee the active development, maintenance, and governance of this large open source silicon project, where we have this tiered structure of committees. We have people with commit rights. It's an actively pruned list. We have a yearly roadmap where we sort of set direction. And then this kind of umbrella, like I said, nonprofit that becomes the maintainer of last resort and an active developer for certain key core IPs. So scalability is really one of the core problems. So we have a very complex secure microcontroller targeting a very high certification bar across multiple national certification schemes that accepts a very high volume of contributions from tens of people daily, and that's distributed across many organizational partners with a lot of different goals. And this has never really been done at scale before. So the question really becomes, and this was very apparent from the start, how do you organize that effort and execute successfully given those challenges? Typical silicon team, you have architects, designers, DV, firmware, software, and there's a relatively organized structure. You kind of know the process by which chips are designed, by which they're produced. That doesn't really exist in an open source context. You have to sort of impose a structure while still, granting that it's open source. People are there of their own free will, and so you have to kind of have this structure that exists that enables forward movement towards this unified goal. It's very, very difficult to actually do. And so the way you do it, the way we do it, is something we call the Silicon Commons. And what this is a collective name for the set of collateral processes, technologies that enable us to do this distributed open source silicon development. So for example, like our set of collaborators basically stretches from Tel Aviv to Taipei, hitting a lot of national capitals along the way. And so it's not just the time zones, it's the culture of the different companies. And so we have to sort of have a unifying framework that brings that all together to get this done. So what this ends up looking like is, when we started, it was, well, we have an open source software model, but that doesn't quite work because silicon is a bit more structured. There's this concept of design verification. Test and design tend to be very split apart. And so merging those two worlds, you kind of end up with this hybrid where we really focus on things like documentation, things like building to the same style guide, things like continuous integration, even developing our own development platforms. So for example, NewAE was actually acquired by lowRISC, and they produce the CW310 and the upcoming CW340, which are the primary development platforms for OpenTitan. We're lucky enough that the design is small enough to fit into a rather expensive FPGA, but still a single FPGA. But someone has to maintain all that, right? That all has to be sort of made available to the partners. It has to be structured and run through a process by which that work gets pulled together. So diving really deeply onto one of the really, really key components is continuous integration. So this is how we keep the design continuously sort of viable while accepting all of these incoming contributions and integrating them into this larger top-level framework. So I think I showed like 9 or 10 of the different groups of tests here. There's actually 17 groups of tests. These all run continuously on every PR. Red ones are failures, green are successes. But this is one of the critical components of the infrastructure that lowRISC is responsible for. So, hundreds of jobs a day, tens of thousands of tests, and a huge amount of compute time. And on top of that, we also do nightly regression, and on top of that, we actually have an on-call regression triage to vector failures to the right people so that we're keeping things current and working, and keeping the database is never fully green, but it's like pretty green most of the time. And we consider that to be it's a pretty high standard, and it's pretty effective. So that kind of takes us from where we came from, and let's talk about where that's gotten us to. It's very complex to build a system like that, to organize it, to maintain it. You could say very reasonably, well, was that actually worth it? Was that necessary? And I would say, without reservation, absolutely. Because we have this RTL freeze, we have our first silicon engineering samples back this year, we have an ecosystem of high-quality IP that is rapidly remixable into new top levels, which I'll come back to. And we also have what has become a de facto research platform that many individuals have used to build on top of. And that ecosystem of IP has been heavily leveraged by others. So first, this follows on from our feature freeze milestone a few months ago. This is, I believe, we hit this milestone a week and a half ago. So since April, we have burned down 28 blocks to greater than 90% pass rate on the nightlies and greater than 90% coverage. So this is what actually gets handed off to our tape-out partner for integration with their backend to turn into an actual chip, to do the layout and turn it into an actual chip. So basically, this whole process is what practically that Silicon Commons turns into, to move these blocks through a structured process of maturation to build a commercial quality design that can then be turned into a commercial quality chip. As I said, this is what turns into the actual chip. We are getting these samples back in probably not August, but probably within a month or two of August. So we have this high-quality, top-level design, built from scratch, known provenance, and then we're turning it into something that is then suitable for development boards, for penetration testing, and that begins basically immediately. But not only that, because the design is developed in the open, you don't actually need to wait for the chip to exist to begin using it. So when I say OpenTitan as a platform, what I mean is platform in the sense of this reusable ecosystem of high-quality IP, but I also mean as a research platform. So this is one of the real benefits of open to innovation is we find and have found over the past 5 years, sometimes in direct collaboration, sometimes organically, that a fair number of researchers have picked up OpenTitan as a design, done work on top of it, and then they've actually fed that work back into the OpenTitan design itself. So this actually puts us very much on the cutting edge of what is, the current set of blinding techniques that people use, or what is the current set of formal verification techniques that people use for fault injection resistance. And that has actually been a real fantastic benefit of doing things in the open. But it's not just research, it's reuse, right? So we happen to know that Microsoft has leveraged the OpenTitan ecosystem for both the Cherry Light tagged architecture as well as the Calyptra server measurement project. So we did a quick analysis, and it turns out that that repository is like 25% OpenTitan IP. And my view is that, and our view is that that kind of leverage is a huge commercial advantage in being able to move quickly at relatively lower cost. So this is open source working as intended. These high quality implementation efforts like OpenTitan eliminate the need for redundant development. They save resources. You never know when priorities are going to shift. And they ultimately kind of foster more innovation that benefits everyone, that benefits the ecosystem, that benefits industry and the research community as a whole. So it's an open source success, right? We feel like we've accomplished what we set out to accomplish 5 years ago, but there's got to be more. We wouldn't just get this far and then stop. That would be a little bit silly, and that is in fact not the case. So we have this roadmap. We've been executing on this roadmap. I traditionally don't show this roadmap with dates, but we're getting spicy with it today. So we've just hit this shuttle freeze date. Talked about that a bit. We don't need to go into it. We are getting those chips back. That's fantastic. The other thing that has not really been made terribly public before now is that we've actually had an integrated root of trust working group running for about a year. And that is actually starting the process of the design being upstreamed now. So that's very cool. We'll go into that in a bit. And of course, we're going to have commercial silicon come back starting 2024. So one interesting thing is we had originally intended to start both an integrated working group and a post-quantum working group. Well, and this again just speaks to the power of open development, is we started going down the path of writing a charter for the post-quantum working group, but pretty quickly we found that we had been pretty somewhere between lucky and smart. I'll take luck any day. In what accelerators we put into our system. And so we were actually able to implement a full post-quantum secure verified boot chain in the boot ROM so quickly that we found that we didn't really need the full kind of heavyweight working group structure. So we implemented Sphinx Plus. This is the stateless scheme. It avoids a lot of the operational concerns of stateful LMS, XMSS schemes. It's aligned with NIST, and this is using an L1 parameter set, so roughly 128 bits of security, also aligned with our RSA3K. And I should be clear, this is just verified boot, right? This is a break glass solution. Should that, that quantum computer that's always just 10 years away happen to happen in the next 10 years. This is not post-quantum attestation. That probably requires additional changes to the hardware. That probably requires additional acceleration in order to do that in a performant way. But what's great about this is our original RSA target was, I think, 10 milliseconds. And so we were able to get a post-quantum verification within, I think it's about 12.5 milliseconds. And I believe also, and again, this is really the utility of doing this in the open, I think Fraunhofer AI-Sec has actually done some work on using OpenTitan and extending it and looking at some of the other post-quantum verification schemes. So we've also gone through and hardened this. It's really just the final comparison, but it is still hardened. And this is something that is going to be shipping in our first silicon just right out of the gate. All right, so it's great that we have this commercial quality design in the open source, but that's not the same as being commercially relevant. You have to be able to purchase the device in order for it to be an actual product. And for that, we need to work with a partner. Turns out to be a partner in the project, Nuvoton, who have a lot of experience in TPMs in particular, but also they have a secure site for development and bring up, a lot of analog security expertise, secure manufacturing expertise, and that's all added value besides the design that you need to actually instantiate and sell OpenTitan devices. Of course, you also need someone to promote it and support it. We're a young startup. We're not going to be making chips ourselves. We're going to be working with others to have those chips made and work with them to promote, support, do field application engineering, all those other functions that require pretty significantly sized and established organizations. So their experience and their sort of presence is really what enable us to talk about offering a commercial chip starting next year. All right, so I've also said multiple times, OpenTitan is more than just a single discrete. It's an ecosystem of reusable IP. Surely I keep saying that for a reason. I don't just like repeating myself for the fun of it. And there is, and what that is I'm very proud to say today for the first time that we actually do have OpenTitan integrated design. We have been developing that for the last year. And that's really, you can think about it as taking the current top level and adapting it. That's not actually what it is. It's really more that we are building from the bottom up, using those individual IP blocks, a new kind of integrated design. So the way OpenTitan works is kind of new official designs have to go through an RFC process. They go through the technical committee. Well, as of yesterday, all of the architecture has been approved by the technical committee for the OpenTitan discrete. So this type A design is a bit more focused on, say, like a chiplet architecture. We actually have a type B design running in parallel that's much more focused on certification requirements, things like the recently released PP, the 117 protection profile, the new integrated secure element protection profile. And what we're starting to do is begin this process of upstreaming. So architecture is complete, RTL, design verification, the draft of that is going to be made public by the end of this year. And the cool thing about this is it actually, because of this comportable, this composable approach we've taken with the sort of strict requirements on documentation and clean interfaces and all of that stuff that comes along with the Silicon Commons, all of that structured development approach, about 80% of the design is actually shared with the discrete. So this allows us to focus on DMA, mailbox. There's some OTP-based ROM patching for the second stage of ROM. So we've split the ROM into an open and a proprietary portion because it's not realistic to say that the root of trust of any modern SoC is going to be completely open. That just doesn't work. We've also had to develop some new methodologies. So for example, taking sort of partner code and extracting it out of their internal databases and bringing it up to our level of standards, visibility, documentation. So we've got a new process for ingesting and signing off on externally developed code that puts it through the same rigorous review process to kind of meet the OpenTitan trademark standards. So this design also supports the dice protection environment and hitless updates, so it's aligned to modern data center needs. But really the point here is that because we took this structured development approach, we were able to rapidly and in parallel develop an integrated root of trust design, which is a very different design space from a discrete chip, and get that out the door. So that's actually the end of the talk. I hope you've kind of enjoyed this review of what we've done over the last 5 years, how we've built this robust, collaborative, open source silicon project, and kind of what the results of that have been. So, and I'm happy to take questions at this point, if there's time.
Thank you very much, Tom, for this nice security presentation. Any questions here? We keep you a little bit away from the coffee, but I think it's worth it. Yeah. There is one?
I think this may be a little silly, but your root of trust of anybody who's not part of the project can get it out of GitHub and you get everything needed for it or enhance it. How can an outsider contribute or use what you have outside the...
There's a GitHub repository. I mean, it's all just there. It's there. It's thoroughly documented. Like, there's a link that says getting started. I would start from there.
So support still happens right inside the group if we need questions. Because root of trust is a pretty... if somebody wants to use it, he needs a lot more stuff than just getting this RTL stuff right. So.
Well, yeah, I mean, you have to pay for that. That's the support and services. No. I mean, kidding aside, it is an actively maintained open source project. So the first thing we tend to tell people is to say, oh, well, who do I email to talk to you about this issue? And we're like, well, you file an issue. Like, you use GitHub issues. Like, it's all... It does exactly what it says on the tin, right? You go in through the front door, you file an issue, and then we actually have an issue triage process where we sort of go through and, do we have to deal with this now? Is this a support question? Like, how do we vector this appropriately? But it is an actively maintained, supported project. That's the low-risk kind of raison d'etre, so.
Okay, any other questions? Then let's thank Dom again. Yeah, a few announcements before you leave the room. So there are 3 talks in the demo theater. You can see them on the screen. And I have to advertise a little bit the posters. So while the booth of the companies are the same as yesterday, all the posters in the corners of the room are new. So please visit them. You haven't seen them. There are posters on HPC, performance computing, AI, open hardware, tools, and verification. So quite some interesting stuff, and the people will be happy to discuss with you about it. So see you at 11:30, I think.